Greeting, ladies and gentlemen. Today we're gonna go through to our sixth question. The torque shown are exerted on pulley A, B, and C, knowing that the both shafts are solid and are made of brace. Determine the angle of twist between A to B and A to C. So, being stated that this shaft in here were solid, questioner want to ask us about the angle of twist between shaft AB and A to C. So let's go to the problem solving. First thing first, like usual, you need to draw FBD. Since that the question A asking from analysis from point A to point B, thus there is the FBD from point A to point B. You will have an 400 Newton meter in there. I'm assuming that will be the mechanical torque being exerted upon the pulley. So we need to compute it into the internal torque. If you took the point of view from this side, then you will see the torque being exerted upon the pulley will have an upward direction, will rotate upward, and the internal torque will have a different direction but have a same magnitude. So it will exert the downward direction. Then we pronounce as T prime. So that is our FBD. Now, the question asking what is the value of angle of twist, which is phi right here. I am using a shearing strain formula, which is shearing strain equal to C times by phi over by L. C that will be in this problem radius for the shaft AB, which is 13 millimeter. You divide by 2, you will get radius. Convert it into meter because you were dealing with Newton meter right here. So we need to make sure all of the length that we were taking in account must be in the same unit. So there you kind of have it right there, 0.015 meter for the radius. The value of length will be remain 1.2 meter because 1.2 because it's already in meter. So the value of phi we don't know. The value of tau maximum we don't know. Mathematically we cannot solve this equation. Thus we need another equation that can find out value of tau shearing strain maximum. So shearing strain maximum, we have another relationship for it equal to tau maximum with respect to shearing stress over by G, modulus of rigidity. Modulus of rigidity been given from the equation 39 gigapascal, which is 39 gigapascal for the modulus of rigidity. Tau maximum, we need to find out. We can find tau maximum by this equation, which is elastic torsion formula, T prime times by C over by pi over by J. T prime C over by J, which is polar moment of inertia. And for polar moment of inertia, in our case, there will be a solid cylinder. The formula that will be pi over by 2 C the power 4. So when T prime in here, there will be 400 Newton meter. The value of C will be 0.015 meter with respect to radius of the shaft. And this value of C in the below will share the same magnitude from the above. So 0.015 the power of 4. Thus you will get the tau maximum equal to 75.4717 megapascal. So you bring this equation downward, then you include the tau maximum over by the modulus of rigidity. You will get shearing strain equal to 1.9352 times by 10 the power of negative 3. Since that we know what is the tau maximum, now we can go back to our core equation. 1.9352 times by 10 the power of negative 3 equal to 0.015 phi over by 1.2. Thus, we will get angle of twist in the form of radius, which is 0.1548. So we need to convert into degree. You times by 118 degree over by pi. This is the answer, 8.87 degree. So for the B equation, which is we need to make an analysis from here to there. So you make a cross-section area from point A to point C. Now we will have 2 essentially 400 Newton meter, 1.2 K Newton meter. So you will have, if you cut from A to point C, then you need to include 400 Newton meter torque with 1.2 K Newton meter. At 100 Newton meter doesn't need to include because we cut it before 800 Newton meter, so that's why we didn't need to include that. Only include these two torque right here. Let's say that just more clear if I cut it in that point. So we only include 400 Newton meter, 1200 Newton meter. So you will have 400 Newton meter, 1200 Newton meter. Now, what is the it is the internal torque for both of this applied torque. To be honest, the direction for the internal torque that will be downward for 400 Newton meter, but in here I'm only I forget to include the direction for internal torque. Essentially, this direction is referred to what we call it, the applied torque. It's not an internal torque, but since that the direction, if we change this applied torque into internal torque, we cannot run from the fact that these two value need to be minus, which is 1200 minus by 400. So it's just gonna be the same thing. So but to be formal, you need to change this direction, which is downward. And for 1200, you need to change into upper direction, because in this analysis we were taking in internal torque. It's not an applied torque, so that's why. But since I make a mistake, then it just doesn't make any difference if I'm changing it into internal or I'm using the original applied torque, because we cannot run from the fact you need to minus 1200 by 400 because the direction were different. But anyway, this is the FBD. Now what is the value of phi AC? That is equal to phi 1 minus by phi 2, when phi 1, which is from point A to point B, equal to 8.87 degree, you need to minus it by phi 2, which is the step to find phi 2 exactly the same as phi 1, but I'm gonna show you how to find it. So phi 2 we don't know, we use the same equation, which is C over by times by phi over by L. Since that the value of C for phi 2, make an analysis from B to C point, there will be 14 millimeter in diameter. Thus, you will have a point 0.02 meter of radius right there. So that's why we have C is 0.02 meter. The value of phi we don't know. The value of L, that will be 1.8, which is B to C. So tau, not tau, but shearing strain, you don't know. So we will be using this equation to find shearing strain, maximum shearing strain. You know what is the modulus of rigidity from the equation, from the question 39 gigapascal. You need to times it by tau. You need to know what is the tau maximum, since that equation doesn't given us. So we need to find it manually by this equation. Tau prime, which is referred to torque. Tau maximum equal to torque prime times by C over by pi over by 2, C to the power of 4. The value of C, that will be radius for this shaft, 14 millimeter. Then it will be 0.024 meter. Tau prime, you need to minus this torque by this 400 Newton meter. Thus, you will get 800 Newton meter. That's why in here there will be 800 Newton meter. And you need to times it by C over by the polar moment of inertia. You will get tau maximum. Then you include the tau maximum over by modulus of rigidity. You will get shearing strain equal to 1.6323 times by 10 to the power of negative 3. Then you bring back the core equation, which is this one. If I tend to find out the value of phi right there, thus you will get the value of phi will be 8.42 in the form of you will get 0.146907 in the form of rate. Then we convert it into degree. Thus we will get 8.42 degree. You minus by the first phi, which is this one. Then you will get 0.45 degree. So that is the answer right there. So I think that's all for today. Thank you for watching and have a nice day. Bye bye.